Hello and welcome back. Let us try to understand multiple linear regression. We have understood simple linear regression where we had only one input variable, the experience, one output variable, salary, and the simple linear regression equation for that is h of experience is equal to theta 0 plus theta 1 into experience. In multiple linear regression, you will have multiple input variables like lines of code, experience, and more. So the generalized, the flowchart is like this. X1, X2, and so on Xn are called as the input variables, and there is one Y. When you feed this data, the linear regression algorithm will actually try to understand the pattern. It learns the pattern, right? When it learns the pattern, it is going to find out the theta 0. It is called as intercept or bias term, and then the coefficient for X1, coefficient for X2, and so on, coefficient for Xn. When you multiply all these and add this theta 0, it will try to generate Y. So when it understood this, when the algorithm learns this pattern, right, you can pass a new record and make prediction. That is called as multiple linear regression. When you have more than one input variable and you are using linear regression, it is called as multiple linear regression. So let us try to look at our data set and how it actually works. So I have taken two input variables, experience and lines of code, and salary is the output variable. I am feeding the data into linear regression algorithm. The linear regression algorithm learned the pattern like this. The hypothesis function for this particular data set is x1 is experience, x2 is lines of code, and the theta 0 it found out is 5890, and then the multiplier for experience is 5301, and lines of code is 0.31. Right? When you feed the data, it is actually predicting that 70,000 is the salary. So let us look at the code example here. So here, I have taken the columns. Let us try to look at the columns. I have taken the lines of code, experience, and salary as the output variable. So when you try to build a model with OLS, right, I am taking salary as the output variable and experience and lines of code as the input variable. So when I am passing the input variables, I need to add them, concatenate them with the plus symbol. In R language also, you need to pass the the input variables and output variables like this only. This is called as formula interface. You need to pass the output variable with the tilde symbol. You need to pass all the input variables separated or concatenated with the plus symbol. Okay, and from which data set it need to pull, and when you set fit, it is going to find out the equation or the model is going to get generated. So the model is there, and I am passing the experience and lines of code and trying to predict here, right? If you look at the prediction for the first record, 12 years experience, 71,000 it predicted, and second record it predicted 79,000. So it is using more features. So the accuracy must be more, or the pattern understanding must be more. This is where the machine learning is very useful. When you have one feature or two features or maybe 10 features, you may be able to predict the target variable kind of accurately. But if you have thousands of features or hundreds of features, predicting it is going to be very difficult for a statistician or a human being. That's when the AI is useful. So we'll see more examples of this in coming classes. And let us look at the summary. When you have multiple input variables, how the OLS algorithm is showing the summary. Let us look at that. So here the R square score did not change. Adjusted R square score did not change much. But when you look at this table, right, we have got intercept, experience, and lines of code, the coefficients for experience and lines of code, the standard error, right, the t-score, the p-value, and the 95% confidence interval. And when you look at the p-value here, see this on the intercept, the p-value is 0.3. On the lines of code, the p-value is 0.7, right? The generally used statistical significance level is 0.05. The p-value for intercept and the p-value for lines of code is greater than 0.05, right? That means we can accept the null hypothesis. What is the null hypothesis for linear regression? The input variable, the independent variable or dependent variable have no correlation, or they are not actually, we cannot use lines of code to predict salary. That's what the p value is saying. Here it is saying intercept also cannot be used, right? That's the p value's importance there. But in the first model, when you look at the simple linear regression, it said the intercept is needed. But when you added this new feature, what is it saying? The intercept is also needed along with the lines of code, because of the p value greater than 0.05. From hypothesis testing, we can say the null hypothesis is true. When I say null hypothesis is true, the linear regression's null hypothesis is the input variable and output variable are independent. We are saying that is true. They are independent. That means the feature is not important. You cannot use, or even if you use the feature, it is not going to create, it's not going to add any value to the model. So here, when we added the lines of code, the intercept also became unimportant, right? When you added lines of code, the intercept also became unimportant. What you need to do is, it's called as backward selection, right? Backward selection approach. So whichever features p value is high, remove that feature and try to build a model. Then the rest of the p values will get set. Rest of the p values will be appropriately given. This p value is getting influenced by this p value. When you add multiple features, one feature will impact the other feature negatively or positively. This is called as interaction effect. Okay, so we'll see that more in our coming classes, but it's just an introduction, and we wanted to see what is multiple linear regression and how statistically we can see the connection between machine learning and statistics. Thank you.